In this video, we're going to discuss the curved arrow formalism, which is a way that we're going to communicate with one another. So our goals for this module are to learn how to use curved arrows to indicate the relationship between two resonance structures, draw curved arrows to indicate the flow of electrons given the reactants and products of a chemical reaction, and then finally to identify nucleophiles and electrophiles. So we can see curved arrows here are certainly important. So let's talk about chemists and arrows. As you know, chemists are pretty picky about their arrows. So I'd like for you to pause for a moment and consider these questions. So everyone's probably pretty familiar with how a chemist indicates that a chemical reaction is occurring. We use just a straightforward arrow like this one. So a straight arrow like that one, where we indicate reactants and products of some transformation. Now, within this reaction, there maybe are several elementary steps. What if one elementary step is reversible? What if A and B come together and they make AB, but AB could go backwards and make A plus B? Well, that would be called equilibrium, and these arrows indicate an equilibrium. These arrows and only these arrows indicate equilibrium. Now, what if two structures are resonance structures? So let's look at some new letters here. Let's say E and F. They are resonance structures of one another. They are two ways to draw the exact same molecule, just differing in where the electrons are located. We would indicate that with resonance arrows, this double-headed arrow. Finally, how do we indicate the movement of electrons? Well, this is the topic for today's video. So this is using curved arrows. Now, when we're showing two electron movement, which is what we're going to be focusing on for this video and probably the entire semester, we would show an arrow like this, where we have it's a double barbed arrow. One electron movement would have a single barbed arrow. So two electrons, double barbed, versus one electron, a single barb. Cool, let's talk more about these curved arrows, which show the movement of electrons. Let's think about what you already know about curved arrows. So you take a second and think about what you already know. Well, you should know how to convert between resonance structures with curved arrows. So we know these show the movement of electrons. We should know that the arrow starts at the electrons and it points at where they're going. Okay, so for example, if we're showing two electron movement, I don't like that arrow. Yeah, chemists are picky. So this would be where the electrons originated. This is where they are going. And that there are two barbs here. That means there are two electrons moving. Awesome, so let's go ahead and practice. So here's some resonance structures, and you should go ahead and indicate with curved arrows how to relate these two resonance structures. You want to look for the electrons that are moving. So these electrons seem to be moving here, the electrons in the pi bond. So I start my arrow where they are and I point to where they're moving. They're moving in between the two carbons. In the next example, we have to put in our lone pairs perhaps. And we don't have to, but we do want to draw in at least the ones that are moving. And putting in all the lone pairs helps us see what's going on here. So it looks like these electrons on nitrogen, they actually become shared here between carbon and nitrogen. And then these electrons in the double bond, that they end up on oxygen, localized on oxygen. So I'm going to start at the yellow electrons. I'm going to point to where they're going. They're going in between carbon and nitrogen. And then the pink electrons, they're going on to oxygen. Finally, the last example, I'll go ahead and draw lone pairs in. It looks like I have these electrons moving here. these pink electrons moving here, and finally green moving here. So let's go ahead and show the curved arrows for this. Excellent. Okay. So the arrows are starting where the electrons originated and pointing to where they're going. Now, I just want to make a point because it's possible that you are wondering if you could have solved this problem a different way. And perhaps you're wondering if you couldn't have taken these electrons and pushed them the other direction, move them here, these here, and these here, to get, this same exact resonance structure, the same exact structure as when we moved the electrons in the opposite direction. And the answer is yes. Yes, you can. You can move the electrons in either direction. I want to go ahead and color code this for you. So now we would have the green ones here. The pink ones would have moved here. And the yellow ones would have moved here. So these are exactly the same. You know, the colors don't mean anything. Electrons are all the same. We can't distinguish between them. It's just helping us kind of keep track of our arrows, our formalism here. But these would both be correct ways to show the movement of electrons. And the way that I know that is that all my arrows are pointed in the same direction. That's how I can check mistakes. So all of the arrows are pointed in the same direction. So for example, it looks like this, right? Or it could look like this. All the arrows are pointed in the same direction, but not having one arrow going this way and one arrow going that way. That would not be right. Let's move on. Let's try to show electron flow and proton transfer reactions given the reactants and the products of these reactions. So again, I might draw my lone pairs in at first because that might help me see which electrons are moving. Okay, so it looks like these electrons are now making a bond to hydrogen. It also looks like these electrons in the hydrogen-chlorine bond are on chlorine. So we're going to start at the electrons and show where they're going. I'm going to start at the yellow electrons, the lone pair on oxygen, and point towards hydrogen. Then it looks like the electrons in the HCl bond, they go to chlorine. So I'll show that as well. Okay, so this first arrow, it indicates what's happening with the lone pair on oxygen, now bonding to hydrogen. We can even color code hydrogen if you want, so you can see that this hydrogen is now over here. And then the pink arrow, it shows how the electrons in the HCl bond are going to chlorine, making chloride. You don't need to understand why this happens, okay, because you're given the reactants and products. Your big focus right now is just draw the arrows that show the electron movement. So let's take a look at another example. I'm going to draw in some lone pairs on oxygen. So this time, it looks like these electrons on carbon are now going to be making a bond with hydrogen. And it looks like, let's go ahead and I think I'll just label my hydrogens color code. It looks like it's that hydrogen, because it also seems like this lone pair, or this pair of electrons between oxygen and hydrogen here on the alcohol, that ends up localized on oxygen. So I'm going to make the CH bond, so have carbon come and use these electrons to make the bond to hydrogen. So that's this first part. And then the electrons in the OH bond, they go to oxygen. All right, let's keep trying. This is a different type of elementary step that you may or may not be familiar with yet, and it doesn't really matter. We can still draw the flow of electrons. So you should pause and try yourself and then come back and see the answer. I'm going to go ahead and draw in the lone pairs, because that might help me see what's going on. I can see, maybe I'll label my oxygens as well. Let's do this oxygen. Here it is. Let's do this oxygen, make it blue. There's going to be a lot of colors on this side. So there that is. Now it looks like the pi bond is going to break. And it also seems like, I told you, a lot of colors, those electrons in the pi bond, those are going to end up on oxygen. The orange oxygen, right? And then it seems like these electrons on the hydroxide, they're going to be used to make a bond to this carbon that I'll just, let me indicate with an arrow. Here it is in both structures. Okay, that was a lot of analysis, so maybe I'll just redraw the reactants and the products of this single elementary step. This happens in one elementary step. And I'll put back in my lone pairs, and now I'm going to go ahead and draw the curved arrows. So we have these electrons on hydroxide. They make a bond to the carbonyl carbon there. So that will form this bond. And I know I drew the arrow coming in from down here, but the bond up here, it doesn't matter as long as you get everything bonded the way that's indicated by the arrows. And then now these pi electrons, remember, they need to move up onto oxygen. So let's show that. There we go. Okay, now how do you know all this is happening? You know because you're given the reactants and products. We haven't learned this elementary step yet. You can't predict the product, like you can't predict these products, but you're given them, and so you can draw the curved arrows. All right, this is going to be our last example, so really, please, please, please pause and try yourself. I'm going to draw in now the electrons, the lone pairs, so I can kind of figure out which electrons are doing the movement. I can see that this bond here is formed. I'm guessing that this methyl is, say, let's use this methyl. I can also see that this bond is broken in this process. And I can see that there's this kind of new lone pair on oxygen. New doesn't mean it's going to be, we're not creating it, it's coming from somewhere. Oh, and I can also see that this lone pair must be donated or used up, and probably used up to make that bond that's being formed. So I've redrawn the structures here so we can go ahead and try to draw in our curved arrows. So it looks like we're going to take these electrons and they're going to make a bond to this carbon, and that results in this bond. At the same time, we're going to need this bond to break between carbon and oxygen because that's not here in the product, and then that's going to result as a lone pair on oxygen. Okay, so we're going to start electrons at the oxygen lone pair, point them to carbon. That's going to make the first bond. And then now the electrons in the pink bond, they are going to go to oxygen. There we go. And so that gives us this lone pair. All right, you will get this with practice, so it's time for you to go practice. Before we end our discussion, though, we do want to define two new terms, and those terms are nucleophile and electrophile. So think about what that means for a moment. What does phile mean? It means likes. So nucleophile likes the nucleus. It likes positive charge. Electrophiles, they like electrons, negative charge. So nucleophile is attracted to or likes positive charges. So something that likes positive charges is itself negatively charged or electron rich. So we're just going to leave it as electron rich. So often you'll see nucleophile abbreviated as N. That's a generic nucleophile, NU. It definitely has some electrons, and it may or may not have a negative charge, but it is definitely electron rich. That's how it likes positive charges. Opposites attract, right? Negative is attracted to positive. Now, electrophiles, they like negative charge, so an electrophile is itself electron deficient, electron poor. It might have some positive charge. So often, electrophiles are represented E+. Okay? So it's a little confusing, but you can do it. Electrophiles, they like electrons because they themselves are electron poor. So they need electrons, whereas nucleophiles are electron rich. So they often donate electrons, are attracted to positive charges. So nucleophiles, they'll donate electrons. Electrophiles, they will accept electrons. They want electrons. So we're going to go back to the examples that we've just been looking at and identify the nucleophile and electrophile. Okay, so for this example here, think about which of these two species, which of these two reactants donates electrons. That's right, this one. This species is acting as the nucleophile. It donated electrons. Which species accepted electrons? Yes, the other one. This accepted the electrons. Now you might look at this species and say, hey, it is electron poor. There's this positive formal charge. I bet this will act as an electrophile. Might be a little bit harder to guess that acetone here would act as a nucleophile, but it does have electrons to donate, and so it can. And as you saw, it did. We will take a look at this example and see if we can identify electrophile and nucleophile. So recall, nucleophiles are attracted to positive charge, and overall they will donate electrons. Electrophiles are electron poor, so they're attracted to negative charges, and they will accept electrons. So keeping those definitions in mind, we can see that hydroxide here acts as the nucleophile. It donated the electrons. The arrow starts at these electrons on hydroxide. And then formaldehyde here, it accepted the electrons. It acted as the electrophile. So we should summarize what we've learned about drawing curved arrows. Be sure that you know where arrows start, where they end, and how you can tell if you've made a mistake. Hopefully you have achieved these goals, that we can now draw curved arrows to indicate the relationship between two resonance structures, that we can draw curved arrows to indicate the flow of electrons given the reactants and products of a single elementary step. And finally, that you can identify nucleophiles and electrophiles. Nucleophiles are often electron rich and they donate electrons. Electrophiles are electron poor and they accept electrons. Okay, time to practice.